Welcome back to another LeetCode slash NeetCode grind video session. So as I promised yesterday, we'll be doing some sliding window question, especially the longest repeating character replacement and also the longest substring without repeating character as well. I want to start with this question because the way I solved it was, its optimal solution was O of n. That was a good solution that I tried solving it, but the way NeetCode solved it, it was much more better. I didn't really pay attention to it that much, but now I will, because now it's going to be useful to me. So I'm going to pay some attention there and see how we can do it. And yeah, just keep getting better at it. And then we have to solve the dreaded longest substring with repeating characters, given that you can do as much as k replacements as possible. So yeah, let's get into this. Let's start a timer, I would say, of I guess 30 minutes, and yeah, let's start. Cool. So we are given a string s and we have to find the length of the longest substring without duplicating characters. A substring is a contiguous sequence of characters within a string. Right. So how do we do this? So let's just take one example and we'll work with that. So we have this. So I would first of all, the way he does it is he has a left pointer. Um, we have a left pointer and we have a right pointer, so to speak, right? So we'll have a right pointer will iterate through the entire list, right? So and our left pointer just will adjust the window, so to speak, so it will be a sizable sliding window. We'll keep checking if there's a repeating character, then it will shut like that. So that's the approach what we're gonna do. And so the very first thing is we would like to loop over this, right? So we would say for I for r in range, actually this is way too small, for r in range of length of s. Like we're gonna loop over this, and obviously our length will be equal to 0, right? And I think the way we will do this is very simply, the way I can think of is, let's say L is equal to 0 and we'll have our result is equal to 0, so we'll say max substring result is equal to 0, right? So I can pretty much say L is equal to result is equal to 0, and I can say substring is equal to, this is just to use that, and we can say for r in range of length of s. So this will keep on going, right? And so what we want to do is we have a substring over here. We'll have a substring over here and we keep checking, right? Is z in the substring? We can say if sr, there are two conditions: sr is in the substring or it is not in the substring, to be honest. So, right, right, there are two conditions that make sense. So agar z nahi hai, like if z is not in the substring, then I think the common sense answer would be you will do substring plus sr, right? We'll do substring and we'll keep length. Actually, you know what, this is kind of confusing. We'll do L is equal to 0, rest is equal to 0, right? So else we would just add this to our substring because this is not there yet and it's not repeating anything. So our substring will now contain z and our left pointer will be over here. Now our right comes over here. Okay, is x in it? No, x is not. So x comes over here. Then we come to y. So our r comes to y. Is y there? No. Then our right. So now is SR in the substring? Yes, it is, and it's somewhere over here. We started our right. This is essentially the substring is. And now we want to wipe out everything, including this and behind this as well, right? And so what we would like to do is, first of all, before even discarding it, we will say res is equal to max of res or length of substring, right? So we make sure we update this, and I can already see a problem with this solution, but and yeah, we'll do that. So this will be, first of all, we'll map this, and then we will say substring is equal to substring, and we would wanna essentially just just not include that at all, and so we do something like substring, we do something like um, find index of Yeah, so we'll do something like substring dot index, and this index will essentially be this plus one, right? So we pretty much make that our new substring, and then we will do substring plus equal sr. I think that makes sense. So what we are doing is we are doing for sr in substring, we find out the max, right? And we say substring is equal to substring dot index of sr, because that's the one that is repeating, plus one. So we take anything including this, and before this is not taken, so we only take whatever this is. And I mean, let me do this crazy. I actually not. Let me do something crazy. Not yet. And we do well. Res is equal to that, and do substring is equal to substring dot index of that plus one, and do substring equal this, and then we continue with this. And I know this won't work, or it does work, but it won't work for all the test cases where no such thing is here. So expect your output. And yeah, the reason for that is we just have to run this one more time. Say this. The thing is, right, if you look at the test case, right, if you run the test case, can you run the test case, please? Okay, for like this test case, I want to do like that, like, because I don't want to use the index. We can somehow store the value. If I, let's say, have this at L, and R keeps on adding stuff, so R पहले यहाँ पे था, फिर यहाँ पे आया, and then यहाँ पे आया, which is great. But if you look at P W W K, L यहाँ पे, R यहाँ पे, R यहाँ पे. Well, now if we remove L wala part, that is kind of dumb. How does he solve it? I do some random. I don't know what I'm doing over here. Yeah, this happens regardless, which is kind of dumb. What was the use of having two pointers then? Yeah, so what is the difference? Why do I have to use two pointers then? I mean, this is the thing I'm worried about. I'll show you. I'm trying to think like LeetCode. So we have P W W. So our length will pretty much access all of the thing. And so we have R and L. Okay, so this is already in the substring, and this could be anywhere. So it could be like A, B, um, W, right? So like, this is much better example. So now our R is over here, and our left is over here. How do we, in a sense, position our left? So let me watch the video solution for this, chat, right? Because I think if I understand this question much better, then I can solve the medium question that we were given yesterday.
Let's solve LeetCode 3, longest substring. So this with algorithm run. Okay, first we'd start at A. We want to get every substring starting at A. So just this one A, well, that doesn't have any duplicates. AB, that doesn't have any duplicates. AC, that doesn't have any duplicates either. And then we get to this first duplicate A. We have two A's now, but remember, we're checking every single substring starting at this have to. Every substring we get after that, like, see how we're doing it? Every single substring after is also gonna have duplicates. So do we even need to check all of these starting at value A? This is the repeated work that we're gonna eliminate with our very fundamental technique, the sliding window. So we want to only check substrings without any repeated characters. So let's actually just do that. Let's make sure that our window, right, our subarray, our substring is always not containing any duplicates. So once we get to this next A, we're going to say, well, now we have two A's. So we need to start removing from the left. We need to start shrinking our sliding window until we no longer have duplicates. So I'm going to say remove this one from our substring. Now our substring runs from here, from the B, all the way to the A. Now it's perfectly valid. Don't have until we remove
I want to see the code, to be honest.
3. So remember the window and our set, meaning it's a duplicate. Then we got to update our window. So we have to take the left character and remove it from our set. So character set dot remove the leftmost character. And then of course we have to update that left pointer, increment it by 1. And we're going to keep doing this while that duplicate remains in the character set. After we've removed all duplicates, then we can just add this rightmost character to our set. And since at this point we know for sure that our substring doesn't have any duplicates, we can potentially update our result variable, which I never declared, so let me declare it up here. Result is initially going to be 0. And now we can update our result, so we can potentially make it larger than it is if the current window size is greater than what it is right now, which we can compute by right minus left plus 1. And then at the end, once we've gone through the entire string, we can return the result.
Yeah, I don't like this solution. Um, I'm using this, saying if SR in substring, and I'm not using this to be honest with you. So if SR is in our substring, just give me 2 minutes. Yeah, I mean, okay, so Actually, you know what's better? We can, even though this is just bad. I mean, over here it makes sense because we're changing it, right? And I mean, this doesn't really. Cool. That's not the main question we were here for. The main question that we came here for was longest repeating character replacement, which is a bit interesting question. And I remember watching the video explanation yesterday, so I'll see if I can connect the dots and we figure out how this is done. So, um, okay, right. What the thing is, we need to find out the longest repeating character replacement. इसका ये मतलब है कि let's say if I could take a good example, if we are over here, right, and let's say just for the sake of entertainment, if I sorry, my bad. If I take this, let's just assume this is my string, for example, right now. What would you replace? Like, in, let's say, okay, some value of one, something. If this is your string, what element would you replace to get the longest repeating character? You would replace A. Why so? Because your A is less in number, and this is the fun part. Like, if you take the length of this window minus the most amount, like the count of the most repeating element, that is B, right? So you have, like, this is 4 minus 3, this is equal to 1. Well, that means over here, that means कि हमारा entire string का length 4 है, उनमें से the most repeating character का length, number of times it comes, it's 3. We are left with 1. That means this, what this 1 means is we have this one element that is in minority, and if we see if this is less than or equal to our k value, that means we can replace it, right? Because k is less than or equal to, that means we k can replace this character to make this of length 4, right? So this makes sense, right? But in that case, if we, let's say, had a string where over here we had another a over here and this was around 2, well, 2 is not less than equal to 1, so even if we used k over here, we wouldn't be able to get the longest string because somewhere it will be discontiguous or discontinuous. And so that is the idea behind it. Like, this is how we'll check if the window that we have is valid, so to speak, and then we can increment some reference. So let me just code this as I go along. We'll have a result page, a result variable, which will store the result of the longest repeating character, right? And we'll have a count, right, which will be in a sense, a dictionary. And the thing we'll do is we'll just keep on going, keep on going, keep on going, and what we want to check is, I think we would like to have a leftmost variable and a rightmost variable over here, right? So we would have something like that. We'll say something like L res is equal to 0, comma 0, and u2 for L in for R in length of S. And so what we would do is we would keep on incrementing R, right, ensuring that this thing is valid, and as soon as this does not become valid, we keep incrementing R. As soon as this become valid, then we stop incrementing. I think that makes sense. I did not. Okay, let's no worries, it doesn't make sense. We are with you, I'm with you. So what we'll do is we have L and R, and we want to make sure we want to get the max of the values. So right now I'm in LR. The only reason why I would increment my R is to ensure that this value is correct, right? Just want to check this. So I think the way we would do this at the moment is um, first thing I would do is I would do count for SR is equal to 1 plus count S count dot get value of SR. If it does not exist, return 0. So this will essentially just take A, and in a map we'll say A is, well, 1 at the moment, right? So this is equal to count dot get SR 0. And now once this is done, we can check something. We can say, well, if, and like one thing we can do is length of window is at the moment R minus L plus 1. Now if length of what we can do is if length of window, and this is such bad spelling that I'm competing with Java at the moment, right? Let's do something like that, right? If our length of window minus max of count dot values, if that is the right way of doing it, let me just check. I think that's the right way of doing it. Let's just see. So if I have like a count over here and I say right, and if I say print max of count dot values, because the count dot values returns a iteratable, it's the max we need to iterate through, we get one. Great. So if this is less than or equal to k, what this means is that this window that we are in is valid, right? It's like, okay, this is valid. And what we would do is we would say, well, we would just say res is equal to max of res, and again length of window, right? So now this is pretty clear. Like if length of window minus max of count dot values is less than and equal to k, um, right, then we know this is correct, that this is a valid window, and then we can just update the rest. But if this is not true, that is greater than k, then we have to make this a valid window, right? And so for that I have to say, I have to keep incrementing r until this becomes a valid window. So we'll say while length of window um, minus max of count dot values is greater than k, right? While this thing is true, what we would like to do is, first of all, we would like to decrement that count because I'm going to go, I guess we'll say count SL is equal to count is equal to um, is minus 1, because that means it exists. If this is it exists, so count SL minus equal to 1, and then I'll say L is greater than 1, right? And so while length of window, so because this will increment this, but we're changing this, so this will anyways change. So while length of window minus max count or value is greater than k, we would like to first of all remove that instance of it, do L plus 1, and while this becomes true, yeah, I think hmm my bad. Right, so if I mean if this is valid, then we'll come over here and this will become our R, and this will become our L. L won't really change. I mean if it's valid, right? If the length of the window minus max of count dot values is less than equal to k, then we'll say result, and then आपका length आगे बढ़ेगा, and then L यहाँ पे रहेगा, फिर से यहाँ गया, सही है, कुछ प्रॉब्लम नहीं, क्योंकि ये क्या है, आपका लेंथ 3 है, मैक्स 3 है, 0 है, then आपका B आ गया. Like I don't know what's the issue over here. Let's figure this out. यही है ना? Wait. So yeah, I mean L comes over here. L comes over here. Okay, and then R will iterate. R right now उधर है, तो R 0 minus 0 plus 1 1 and ठीक है. So length of window 1 minus 1, right? क्या ये less than equal to k है? क्या 0 less than equal to k है? Yes, it's equal to. Then we'll say result is equal to max of result equal length of windows. ठीक है. Now क्योंकि ये run हुआ, it will run again and ये हमारा r यहाँ पे आ गया. And again we say okay, count 1 minus 0 plus 1, so 2 हो गया. 2 minus 2 minus 2 0. ग्रेट. सो अब यहाँ पे आ गए. ठीक है, सही हो रहा है. ठीक है, प्रॉब्लम अभी भी नहीं है क्योंकि इट्स फाइन. नाउ वी कम टू दिस, राइट. नाउ अब इसका लेंथ कितना होगा यहाँ से? 0 1 2 3, तो 3 माइनस 0 प्लस 1, 4 लेंथ हो गया. अभी मैक्स एलिमेंट का क्या है? 1. सो क्या 1 लेस देन इक्वल टू के का वैल्यू है? हाँ, के का वैल्यू है, राइट. सो वी डू रेस इज इक्वल टू. ठीक है, नाउ वी कम टू ए अगेन, राइट. देन वी कम टू आर, राइट. अब ये हम लोग का विंडो हो गया. 1 2 3 4 5 6, 6 माइनस 1 2 3 4 4 2. नाउ क्या ये, सो दिस, सो राइट, राइट, दिस इज इक्वल टू 2 which is greater than. So now क्योंकि ये आपका आया वैल्यू, फर्स्ट ऑफ ऑल बी का वैल्यू तो मतलब बड़े होगा, मतलब बी का वैल्यू यहाँ पे 2 होगा एंड ए का वैल्यू यहाँ पे 1 2 3 4 होगा, राइट. एंड सो यहाँ पे क्या होगा अब, क्योंकि वाइल लेंथ ऑफ विंडोज माइनस मैक्स काउंट डॉट वैल्यूज आपका 4 आ रहा है जो ग्रेटर देन के है. what we will do is we will do count SL. so we will say count SL which is a का काउंट हम लोग कम करेंगे. तो a का काउंट कम किया तो अब यहाँ पे आ गया, राइट. एंड दिस अगेन चेक्स. आई थिंक कुछ यहाँ पे गलती हो रही है, बट ठीक है. एल यहाँ पे आ गया एसेंशली, राइट. एल आपका भर गया एंड देन हम लोग फिर से कैलकुलेट करते हैं लेंथ ऑफ विंडो. सो 1 2 3 4 5, 5 माइनस मैक्स एलिमेंट 2, तब भी ज़्यादा है तो लेंथ यहाँ पे आएगा एंड 2 का आगे 2 होगा, राइट. एंड सो वील हैव 4 minus 2 which is 2, which is again big, and so we held L over here. And इसमें प्रॉब्लम कहाँ आ रहा है? I just went through the entire loop. प्रॉब्लम कहाँ से आ रहा है? एंड ये बोल रहा है कि especially this string index out of range. Count SR 1 plus, okay, that makes sense. Length of windows R minus L plus 1, that also makes sense. I'm so dead right now, like I don't understand, because I'm assuming when I do L plus 1, or should I do something like, oh wait, should I do something, this is gonna be bad, but I feel like if I do, that shouldn't change anything. It does. Okay, so I think it was a scope related problem then, because I was like, I ran through the entire iteration. Okay, interesting. So I don't even know Python properly. um, but yeah, pretty much that's what happened. So okay, I think what we should do is just run through the iteration one more time, I guess, just to get my hang of this. So let's go through this again. Let's run through this. Let's take this away. Okay, so we'll have a map over here. So A का map अभी 1 होगा. So we have L R, because the reason why we're not decrementing this is because we'll be repeating the strings and that will be infinite loop. हम लोग R L को बढ़ा रहे हैं. And why is this meant to terminate? Well, even if it doesn't, if the string becomes like 0th length, um, you know, so this makes sense. So if the length of window minus this is greater than or equal to k, then we can obviously use k in this, and that means this is a valid window to work on, right? Also, right, while, so then we do a while loop, obviously for good measures. Why I'm doing sliding window? क्या खोल रहे हो आप? कुछ तो बगी हो गया था. I was opening sliding window. Yeah, let's see his code. So yeah, so length of, oh wow, his code is much simpler, so to speak. Yeah, right. And then he says, well, count SL is equal to count SL minus 1 L plus 1. Weird approaches, because I did it like this, because this essentially this loop ensures that the time this comes out and comes again, like this will run. But the thing with this loop is it still may not be the case. It's pretty much emulating a while loop if you think about it, right? If I could think of that. Count. Okay, I just want to look at the video solution again, because why not? This is O of 26.
What happens when we take our left pointer, for example? We're going to be, since we reached another B, we're going to increment the count of B to 2 now. And so the length of our window now is 4. And the count of the most frequent character is either of these, and that's going to be 2. 4 minus 2 is equal to 2. Is that less than or equal to K? Length 4. And so once again, this now is 5 minus the, because when you look at our window, we have so let's take the size equal to number of replacements for our window until we are valid. So we're going to take our left, going to be at the B. So since we remove,
Yeah, so the moment we come out of this loop, we will definitely hit this condition which we calculated.
This A from our window, we have to decrement the count of A in our window. So I'm going to cross this 3 out, window valid. Well, the size of the window now is 5, and the count 3 is going to be, so this is technically a valid window right now. Way you can do it without having to a substring that we by the count of the most, and we can do that just like this. And this is a constant time operation. We're not scanning. What we obviously do is update our do while just because. So while the window is not valid and we max value from it. So this, and that is the entire algorithm.
What? He does the same thing as that. Oh, well,
After all of that is done,
that's funny. Yeah, I see what you're trying to do. You essentially would just run this. It's also valid. Oh wow, gलत some scoping issues, I would say. Yeah, I don't know what that is. I mean, nice. I want to try minimum window substring because I'm so confident, right? I mean, I was not able to solve this by myself, but I see the logic behind it. I mean, it will eventually stop at R, right? It will eventually stop at R, so that works. It's a hard question. I don't think it's a hard question. Trust me, chat. I have seen a lot of hard questions. That's not the same one of them. Um, okay, let's read through this, I guess. Let's put up a 30 minutes timer and let's see if oh no, there's some sound in the background. God help me. Anyhow, let's see. Given two string s and t of lengths m and n respectively, return the minimum window substring. A substring is a contiguous non-empty sequence of characters within a string of s such that every character in T, including duplicates, is included in the window. If there's no such substring, return the okay. Let me just open up Xcali draw, obviously. So we are given two strings s and t of lengths m and n, respectively, and we need to return the minimum window substring of s such that every character in T, including duplicates, is included in the window. Okay, let's look at some examples because so this is our s and this is our t, and we are given b and ca, which is you can see over here, and the minimum window substring b and ca includes a, b, and c from string T. We have a, we have a. Both A's formed from T must be included in the window since the largest window. Okay, that's what you mean by that. That's what you mean by that. So, so you're trying to say ki it has to essentially include the entire T contiguously, right? Oh wow, it has to do like that. Okay. So by this very logic, right, if S's ka length is equal to M and this length is equal to N, the only way we can find a substring that includes every element of n, including duplicates, is if n, I mean, this is one of those conditions that may not be true, if n is greater than or equal to n, right? If m is less than n, then this is too impossible because because let's say we have a and this has only like b or some a, well, the number of characters we need n to be in m utna length hai hi nahi uska, so this wouldn't really work, right? So I think we can do that predominantly check, but I don't think that they will do that, right? I mean, one thing we could say, if length of, right, that makes sense, and then we can else just return something like that for now. That's like the common sense solution at the moment, like just think of some edge cases. When you see it runs certain like on a certain thing, like this makes sense, right? But for the other test case when this is not true, we need to figure out a way where we can look at s and we can provide it the minimum substring that includes all of the letters of T. Okay, so I guess we'll just do with this. Let's open this. Okay, let's remove that. um okay, so essentially, um okay, so this is our s, so to speak. Okay, and right, so that's our s and we want to find it. How would we want to do this question? Uh I guess the way I would like to do this is have the T in a sense, because I want to find every element of T, including all the, I mean, so I can look at A and S. Does A belong to T? Does A is in T? Well, I guess that's checked off. T is not here. So does that mean do I stop looking? Um, no, because we could find a minimum substring. We could find something like A. We can find something like A, T, C, B. We never know. So we just come here to O. Well, O is there. No. Is B is there? That's great. B is there. Wow. Is E there? No. Is C there? Well, now we have checked up all of them, and this is one of the substrings that we were able to find. And so, boom, this is pretty much added to this variable that keeps updating the min. Now the question is, where do I start the window from? Should I start the window from here and start a fresh substring, or should I start from the window from here? Right? That's a valid question to ask because I started from the first element. I sound like a nerd. I started from the first element, and the reason why I stopped is because I found all the elements. Um, or return the substring as well. Yeah, the reason why I stopped is because I was able to tick mark all of the ones that were in T. I could make like a hash map. So itna one we have, right? Like I could do something like elements. This is like this for so for ch in T. Um, mm, um, how do you do that? By the way, I just forgot. I'm so sorry. I just forgot how you do that. How do you do that? Okay, count dot get lech. If you don't get anything, then 0, right? That I think that as far as I can see, that's going good. um right, so we could first of all we just make lech ch. Why is this? Ah, man, come on, let's not do this. um okay, and le dot get le dot ch and 0, and yeah, so that essentially gives us this hash map, so to speak, to work with. Cool. And so now we can focus on S. So I start at S and I see whether the first element is present in the dict, right? And while it is not present, I won't even start looking at the string, right? Because if I look over here in this D, well, I don't really care because it's not starting with something I don't really need, right? So I just skip ahead. But okay, it's A. So now I will start checking for substrings because I see this. So I see, well, D is not here, O is not there. So how do I terminate? I mean, the worst case is we reach the end of the list, or we check out all of this and we're like, oh, well, that's one substring, and then that's great. We put that to another counter. And, but then how do I start it though, right? If you think about it, I mean, okay, let's take, how do I take the smallest example to work with? Um, Maybe this is the small example, but that's too small. Um, okay, let's take that example. I think the smallest example of it. So S is equal to A, and wait, the one that was there. S is equal to this, and this is equal to this. Right. So first thing is, after we are done there, we will make something like A is 1, and we'll start on the substring, right? So if the start of the substring is present over here, well, that's great. So now I can decrement this by 0, right? And then I can go ahead, but then I stopped. The reason why I stopped instead of stopping at the end of the list is because, well, all of the elements have been touched in the substring. That's why I stopped. Okay. Hmm. Okay, the kids outside are having fun. I hope they never have to do LeetCode in their life, but so why is it like this? Why are you like that? What why is it like that? Anyhow, so I guess I'm just like thinking about I mean right now I don't even know how to solve this, to be very honest. I don't even know what to do with this because I'm a bit confused myself. um, I mean, so okay, so after we are done iterating, we would do something like one. This is our count map, so to speak. I start with a. So okay, let's start building out something, I guess, over here. So I start from the element that is present. If it's not, then I'll just go ahead with the next one. Again, we'll have a left and a right pointer. Right, is this okay? So this is starting. So great. We'll now just increment our right pointer. Right, this is not there, this is there, great. This is not there. Oh, this is there, great. So that means this is one of those valid substring that contains of them. Now whether this is minimum or not, I don't really care, I don't know. Right, now I got this substring, but how do I go ahead and check for newer substrings? Because यहाँ पे the actual solution for this is b and ck, this substring. So now that I'm done with this substring, I could most likely just come to d and start checks d substring, um, which would be very bad in terms of time complexity. Or I could start from here, but I don't start from here, and I come over here. I don't start from here. I come over here. I don't start from here. Oh, I come from here, and because this contains this, and I just go on, and then I stop. Could be, could be. Okay, let me do this some another time. So we'll do something like count is equal to this, and we'll say for ch in t, count of ch is equal to 1 plus count dot get. Is that how you do this? You sure, chat? Because I'm getting. How do you do that? Count dot get sr, count ch, and nothing then 0. Obviously, then we obviously remove all of this. This becomes obsolete. Chat, I think I may know the solution, but I don't think LeetCode will give me enough time to implement that solution, which is kind of sad. So this is done. This is great, right? Let's also do L is equal to, actually let's this is, we're gonna keep this close nearby. Let's go substring is equal, so we'll do something like substring is equal to ring, and we'll say L is equal to 0. So we'll say for R in range of length of um, mm, right. The first thing we'll do is if SR um, not in count, right? So I don't want to do anything. I'll just continue to the next, right? So if SR is not in count, and I'm just to be more explicit about this, I will most likely say keys. I think by not in dict will check if not in the key element in Python. I think that's how it works. Yes. Okay, yeah. Okay. So it will check whether it's in the count value or not. If it's not, then we don't. Right? For right, that means this is promising, right? This is promising, right? And so what we would do is I would like to make a copy of this so that so so because the thing is we did the layer, but then we're gonna check the again, right? So what we would do is we would make a copy of count. So cc of count, um, count dot copy, and what we would want to do is what do we want to do, like, because right now we are at a, and a is certainly in it. We want to do substring plus equal, obviously we would like to do that, like to equal sr, right? Actually, let's not use the while loop because I'm a bit fragile with it. Let's just yeah. So if this is in this, right, then we want to start calculating the substring while while what? So we want to say L is equal to R. Um, um, right. L is equal to R, and so while I want to keep calculating this while K. I want to keep calculating this. I mean, I'm thinking like something like if the max of count dot values is equal to 0. Um, 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 I would assume that's how we do it. Dot values is not equal to 0, or like we want to continue this until we have pretty much relinquished all of them, right? I mean, I want to do that, but this will, I mean, we'll worry about that. We'll worry about that. S is not out of bound. Um, and so so oh my god, this is just painful, yeah, to be honest with you. um yeah, so while max.count.values is not equal to 0, we are at L is equal to 0 at the moment. um to be honest, this is like very lousy. um right. I mean, while it's, I mean, to be honest, because our aim is to decrement it. So um if it's in the dict and if it's not already equal to 0, then we decrement it, right? I mean, that's the thing. Because इसका अभी भी बड़ा है, then we would do right, we would do minus equal 1, and so here this would just become 0 in the C copy, right? If it's not in the C array, don't really care. Uh, I think right now we'll just do something like an array of sorts, and we want to keep something over here like an ss is equal to this, and um, what um what's the issue over here? This is a simple code, right? Ah, my bad. No, actually not my bad. Actually, should I just do ch? I think I did ch. My bad. My bad. My bad. Ah, and my bad. My bad. Um, that's how it works, right? Like if I have like let's say a bunch of substring array, which is bunch of A, B, B, C, something like that. I mean, it should work, right? Min of substring. It should give me something like that, I would say. Yeah, so wow, okay. Yeah, so it passed this test, but didn't pass this test. Okay, let's see what my code does when it's exposed to this. 4 minutes. Ah, Jesus. I don't think in 4 minutes I'm able to do anything. So A is 1. Um, um, What? Man, that's the thing, right? I mean, the thing was, it's not giving up the minimum value, which is kind of weird. But it should give me the minimum of the substring. Ah, I think I figured out what's wrong. So the terminating condition can be either that the end of the list happened or that happened, right? I understand what happened. So the thing is, the reason why this could terminate, and so I will, if max of c dot copy dot values is equal to 0, then only I will append it. Else I'm not doing it, right? Um, wait, yeah, that's why I'm only appending it. Other than I'm not doing anything. What? Okay. Again, B and CA, and that should worry about, like, if only the values is, because I don't know what actually terminated, right? If it's equal, then only append it, or else just don't, right? Yeah, I mean, okay. um BTA, and then most likely my algorithm is like, okay, we'll start from here then, and this terminates, right? Yeah, so BTA, start from here, right? um oh no, why would you do that? Okay, chat, I think I've exceeded over time, and I'm just gonna look at the solution, even though let's just say I was able to kind of get to a point where I was like, okay, I think I can understand this, but I think I'll be wasting more time looking at this than doing anything. So even though this, start from here, why? My code is again messy as hell, so I don't want to really delve into this anymore. So
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve minimum
it
window
it
substring. We're given two strings, S and
it
T,
hurts
and
me
we
so much
want
that
to
I'm
return the
this
minimum
close.
window in the string S, which contains every single character that exists. There happens to be a shorter string that has we're going to output. So what's even a brute force way to solve this? So we're given S and T, right? And we want, like, if we're checking a substring, right? Like this substring, maybe this is our solution, right? How do we even determine that? Well, let's use some hash maps. So these two are our hash maps. You can see I have one for T. What does this hash map represent? Well, you look at T, right? Because for each of these substrings, we just want to make sure that it has at least one A, right? One A, has at least one B, and it has at least one C, because that's what we have over here. We just want to make sure that we find the minimum substring in S that satisfies this condition. So for every possible window that we check in S, like maybe we check this window, we are going to want to have a hash map for the window, and we're going to count how many A's do we have. Initially, we're going to start with 0, right? Because initially our window is going to be just empty or whatever. We're going to start with 0 B's and 0 C's. But for this current window, you can see we have 1A, 1B, and 1C, right? So we have 1A, 1B, and 1C. So as we compare, right, we compare how many A's do we have versus how many do we need, right? This is how many we need, and this is how many we have in our current window. You can see we need one and we have one, right? So the relationship we're looking for is greater than or equal, right? We want the counts all to be greater than or equal. But one thing you can see is brute forcing is going to be difficult, right? So let's say we initially start with this window, right? We see we just added an A. So what are we going to do? We're going to
Welcome back. This is part 2. I mean, even though you will see the video as a sequential, like in a single video, but I was not able to go ahead with the NeetCode video, as you can see by the time difference on my laptop, because my house, let's just say, I was not able to find a place where I could study quietly, so that's why I had to study now this late at night. You gotta do what you gotta do. We were doing minimum window substring. Before I do this, I would like to do. I mean, yeah, let's just do this. I was actually on the verge of like watching the solution video because I had no I didn't know how to solve this, to be honest, right? So we'll just watch the solution video of this and see what we can do. I really tried solving this. As you know, like 30 minutes, I did just like put my head down and try to solve it, but I was just not able to, sadly. Let me just revisit this. So, I mean, I would just be clueless, to be honest. So I'll just watch the video explanation and as and what's this? So let's go. We can use go. So you can say func min. Yeah, go.
looking for is greater than or equal, right? We want the counts all to be greater than or equal. But one thing you can see is brute forcing is going to be difficult, right? So let's say we initially start with this window, right? We see we just added an A. So what are we going to do? We're going to update this. Now let's just check, is our window valid? Well, we have at least one A. And so remembering
So greater than and equal to. Yeah.
this is how many we have in our current window, and this is how many we need to satisfy the condition. So initially, let's start with this window, just 1A. So then we can update our count for this window, right? Add a single A. So now my question is, have we satisfied the condition? Do we have everything we need?
Not
So
yet.
how are we going to check that? Well, we have to check all of these, right? So is the have count greater than or equal to the need? Yes, it is. What about this? Is the beat count greater than or equal to how many we need? The answer is no, right? So therefore, we don't have how many we need. So therefore, we have to actually expand our window, right? We have to add another character, this D, right? But that's not actually going to update
Any
our
of that, yeah.
window because we don't need
Yeah, that's what I tried doing. Uh, I tried actually adding dict, but yeah, the way I solved it was, I mean, it's like this is the solution I came up with, but let's just say not that interesting. As you can see, I had a C copy which checked for this. I don't even want to look at my code. It
any
was so
characters
bad.
other than A, B, or C. So we
Yeah.
don't really care about the D. The same thing is true for the O, but now we have a B, right? That's good because we do need a B, so we add a B. So now we're going to have to run the same operation. Do we have everything that we need? So we're going to be doing some repeated.
Yeah, that's true. I think we want to do that. Merge two sorted linked list together. I guess, yeah, we would like to do that, to be honest, because you need to like recall those things as you do, right? So, um, just for the sake, just so I remember it. Okay, sorted linked list. I think I'll do these 3 questions just to get a hang of it.
Work. Do you notice this repeated work we're doing? We have to check if we have enough A's, which we know we do because we already checked that when we first added this element. So we notice we do have enough A's. Do we have enough B's? Well, this time we actually do because we just added a new B, right? That's the most recent character we added. Great. So we know we have enough B's. Do we have enough C's? We do not have any C's in our string. The count is 0. Therefore, this condition is not met. So we do not have our result yet. We have an A and we have a B, but we need to add more. So now we're going to add an E, which we don't really care about. We're going to add a C. So finally we can see that we met our condition, right? But with our current algorithm, our brute force way, we have to repeatedly check every one of these, even if we already know the count is met. So this is basically where our repeated work. This is what I'm going to show you how to eliminate. But as you can see, we have enough A's, we have enough B's, we have enough C's. So therefore, this is a possible result. It might not be the minimum, but it's a possible result. And what's the length of this? It is 6. So we can say for now that our result is length 6, and it goes from index 0 all the way to index 5. So I'll put 0, 5. That's our current result. So one thing we noticed is we're having to do a lot of repeated work to check that we have everything that we need. We have to check every single one of these characters, right? But we know we don't always have to do that. So let me...
Okay, so this is repeated work is again just looking through checking character then greater than n. Good.
Show you how to do it without repeating all that work. We're going to start out the same way. So we're going to add an A, right? That's our first character. So now we're going to check. So now what we're going to say is A count is 1, right? So now my question is, do we have to check every single one of the halves? Because initially we know that none of the conditions have been met, right? Initially we start with all zeros.
Yeah.
We also know that the number of characters that we need is going to be 3, right? Meaning we need to satisfy the count condition for 3 unique characters, right? And we know that we start out with a have value of 0 because we know for each of those 3 characters, we have met the condition for none of them, right? Initially, we met the condition for none of them because we start out with all zeros. But now you can see we just added an A. So let's check just for this one character, have we met the condition? Is the count greater than or equal than 1? Yes, it is. We have 1 and we only needed 1, so we met the condition. So what does that mean? We can take our have value and update it. So initially it was 0, now we can change it to 1. So now we have 1. But my question now is, have we met the condition? Well, we need 3, but we only have 1. So we haven't met the condition. You can see what I'm doing here, right? Before we needed to check the condition for all 3 of these each time. Now we only have to check the condition for 1. We have 1 value that tells us how many we have. We have 1 value that tells us how many we need. So before we had to continue running an operation of length t, which is in this case 3, but who knows, it could have been bigger. T could have been 10, it could have been 100, it could have been anything, and we would be bounded by that. But in this case, we only have to do 1 operation for comparing these integers and 1 operation for comparing the integers of the character that we just added. So for each character that we add, we only have to do an O of 1 operation. So now let's add another character. Let's add the D. We know that doesn't really do anything. We add the O. That doesn't do anything. We add a B. This is good. So how am I going to do things differently this time? Well, like usual, I'm going to change this 0 to a 1. We know we have 1b. So now I'm going to check, has this condition been met, or is it equal? I know last time I showed you greater than or equal, but really what we're looking for is, are they exactly equal? Because that's when we know the condition has been met. So if these are exactly equal, which they are in this case, 1 equals 1. So what that means is we can increment our have value by 1. Before it was 1. Now we're going to actually change it to 2. And now let's check, are these equal now? Do we have what we need?
Um, it's essentially need is the length of t, right? So to speak. It's like we need, I mean, he said three distinct characters, we need the length. Um,
It's not because 2 is less than 3, so we haven't met the condition yet, so we have to continue. But notice how that was an O of 1 operation. We just had to make one comparison here and then one comparison here. We didn't have to go through the entire list. So now we're going to add an E, which we don't really care about. Now we're going to add a C, which we do care about, so let's update the length of this. Now, are these exactly equal? We know we just met the condition for these last two. Now, have we finally met our last condition? And yes, they're both 1, so we can take this 2 and replace it. It's getting a little messy, but I hope you can
yeah,
see.
okay, it's essentially how many elements have we ticked off?
We have a 3 here. So now let's have exactly what we 0 and 5 and right. So now what are we going to do? Are we
Yeah,
just going
now,
to keep adding elements again and again? Well, we want to find the minimum, so let's at least try to find a string that's less than 6. So what are we going to do? Let's remove the leftmost character and keep doing that until this condition is no longer valid, until we don't have what we need anymore, so we can try to at least find a smaller result, because ultimately we're looking for the minimum string. So I'm going to take this character and remove it from our current window. And so we're removing an A. So what that means is we have to update this. So it's no longer 1. We actually have a 0 for count A now. And now we know that this condition is conditions met, right? These keep looking for the minimum. So we add an O, but we know we don't care about that. We add a B over here, right? We do care about B. So what are we going to do? We're going to take the B count. It's 1 currently. Now we have 2. Now that's great because we actually have more than what we need, right? We need 1, but we have 2. So am I going to take this and update it? No, because they're not equal. What that means is we added an unnecessary character. It's okay, but it didn't help satisfy the condition. We already know this and this were satisfied. This is the one that needed to be satisfied. So since it's not exactly equal, we're not going to increment our have count. So now let's add another character, the A. We equal. Have we met? So we update what we need, so we potentially found a result. Now the only problem is this result goes from, but now we want to try to find an even smaller substring than this. So let's start populate our window and let's just keep popping values until this condition is no longer met. So now let's pop a B. So now we have to update our value of B. So this was originally 2, now it's going to be set to 1. So now it's set to 1. So did we tell this condition is no longer met? So now let's pop a B. So now we have to update our value of B. So this was originally
I don't understand it.
only 2, now it's going to be set to 1. So now it's set to 1. So did we undo this condition? Is this condition no longer valid? Nope, because this is still greater than or equal to the count that we needed. So the condition is still valid. We don't have to update our have count yet. So actually, this string is still a possible. These two are still valid. This one is not valid. We have to update our have count. So our have count was 3, but now we removed 1, so it's going to be 2. So now it's no longer equal, so our string is no longer valid. It's length 5, but it doesn't have another valid. These are once again equal. So since they're exactly equal, that means we just now have met the condition. So we met one more condition. So we can update our have count now to 3. That means it's exactly equal to this, right? Time, because you see we added each character once. That's an O of 1. We removed each character once. Every time we added or removed a character, we did at most 2 operations, right? Which is, our string is, because that's just how they want us to handle it in this problem. And I'm going to have 2 windows that I showed previously. So count of t and just the current window that we have. They're both initially going to be hash maps. They're both initially going to be empty. And the first thing I want to do is initialize our count t map, because we know this map actually isn't going to change at all. So for every character in string t, I'm going to add 1 to it, but the value I'm going to get, I can't just do this because it's possible that C hasn't even been added to count T yet. So I'm going to do some Python stuff. I'm going to use the function get, which is good for this. So I'm going to get C. I'm going to get the count of C. So if C exists in our map, it will give me the value that's stored in here. If it doesn't exist, I can put a default value, which is going to be 0. So if it doesn't exist, this function will return 0. So that's just a way that I like to handle this case. So now that we've initialized the count of t, we can have our variables have and need. So we know have initially is going to be 0 because we have 0 of the characters we need.
It's length of t.
Need is going to be initialized to the length of count t, because that length of count t gives us the unique characters in the string t. And then I'm just going to start iterating through every character in S. So I'm going to use a right pointer for that. The R is going to tell us the right boundary of our current window. So I'm going to get the character that we just reached, which is S at index R. So I'm just going to put it in a variable C. So with C, we know we can update our current window. So I'm going to do window of C and add 1 to it.
Okay, that understands it. C is equal to SR.
For the character that we just reached. And here I'm basically return 0 with this function. Now we want to know, does this count completely satisfy what we were looking for? Does window
So C is equal to SR.
C equal exactly count of t? That means we just satisfied a condition for the first time. But one thing I also want to check before I check this, a condition for
Windows C is equal to count to C
the
if you
first time. But one thing I also want to check before
think.
I check this is that C is even a character in count T. So if C is in count T and this is true, because we know we don't actually care about characters that aren't even in the string T to begin with. And we know if this is true, we can update our have count, so we can increment it by 1. This means we just satisfied a condition. So now what we want to know, does have equal need? Exactly. So are they our result potentially, right? So if we found a new minimum result, let's update. So this actually reminds me that I didn't even set a result. So let's set like a left and right pointer. So I'm just going to give it a default value of negative a result. So let's set our left and right result length. So initially we know our result is going to be a pointer, like a left and right pointer. So I'm just going to give it a default value of -1, -1. And for the result length, I'm going to put float infinity, because that's a good default value in this case, because we are looking for the minimum string. So any value will obviously be less than infinity. And I'm also also going to initialize a left pointer because we know R tells us the right pointer, left pointer will initially be set to 0. But so now we can actually update our result. We know the condition has been met. So if the current length of our string, which is going to be R minus left plus 1, this is how you just calculate the size of our current window. If it happens to be
Okay, chat. I'm gonna stop because this is not like hitting me in my mind like at all. Like I think maybe I think I'll do this tomorrow to be honest because I'm not able to get this at all in my head, sadly. It's kind of sad. Um, you know, it's one thing when the hard question just starts. Uh,
then
I mean, I don't know what to do to be honest. Yeah, I mean, I just solve these questions that I promised that I would do. And okay, I turned out Docker desktop. Great, Docker desktop is turned out great. Just playing Valorant with my friends. Okay, let's just solve this. Okay, so how do you merge two sorted lists? So the first thing we do in order to merge a sorted linked list is fl um, oh it opens a printer. Let's see. um, right, so the way we do this is quite simple. For the way things are done, we'll have a dummy node. So we'll say dummy is equal to list node. We'll say tail is equal to dummy. Now we want to sequentially compare both of the list items. So how will we do that? It's quite simple. We would pretty much say, okay, while L1 and L2 is there, if L1 dot val is less than L2 dot val, we'll do something. Else will also do something. Right. So if L1 dot valve is less than L2 dot valve, we will say tail dot next is equal to L2 L1 sorry L1 is equal to L1 dot next, so we can compare the next element. Same thing over here, tail dot next. This means tail L1 dot valve is greater than or equal to. If it's equal to, doesn't really matter which one you put. So we can say L2 is equal to L2 dot next. And the time we come to the end, that means that by this very understanding, they will have a node. So we want to do tail is equal to tail dot next. Um, yes, now tail is pointing to the next, right? And what could happen is if any link, if L1 is not none, we can essentially do tail dot next is equal to L1. If L2 is not, we can say tail dot next is equal to L2, and then we can return dummy dot next as our head. Let's see if this runs. Okay, so how does this work? So we have a dummy node, and this dummy node is pointing to God knows somewhere, right? And we have a tail node that is also pointing over here somewhere, right? And so what we do is we start comparing all the list elements, right? Yeah, so we compare all the list elements of this L1, this is L2. So we do tail is equal to tail dot next. That makes sense. Go to the next question. Reverse linked list is easy. uh why again this thing is misbehaving. um um okay, reverse linked list is easy. Reorder list, the way we reorder it, um it's initially set Merge k sorted list. I mean, right? That is too easy. It's a trivial. Sliding window. So best time to buy and sell stock. Okay. Longest substring without repeating characters. Longest repeating character replacement. So we have count and we have res. Okay, so we say for r in range. Count sr length of window is this. Now length of window minus max of this. So that means this is a valid, and we can say result is essentially equal to this. Else we just um, else what do we do? Um, what is happening? Um, Else we just say count this L plus 1, and then this comes again. One of In all of these questions, especially I see we always popping off from the left and we just keep moving right. So we just say we just okay. Minimum window substring. I mean, I don't know, man. Longest repeating character replacement makes sense. There's a way of doing this. There's another way of doing this, but okay. I've never felt this lost before, to be honest. But I just want to do a different question, to be honest, because sliding window is, to be honest, is sliding my happiness away. So, yeah, we are back. So we're gonna solve this question in the binary search, because I just don't think I'm that good at sliding window at the moment. I'm not being able to understand certain aspects of it, so I'm just not gonna do it at the moment. I'm just gonna stick to binary search and see how we can do this. So we have this question. First of all, we know how binary search works, the algorithm for binary search, right? How binary search is essentially working, right? So we'll have a high, right? So we'll have a left pointer which is equal to 0, and we have a right pointer which is length of the array, right? And we say while length is greater than or equal to r, right? And we say middle is equal to length plus r pi by 2, and then that decides all of that. And this is our basic binary search, provided that the array is sorted. So now we have a question which says search in rotated array, right? So let's read this, and I think let's start a timer. As this is a medium question, we'll start a timer of 25 minutes. If I'm not able to do that, then we have to see a video on it, how to solve it, try to conceptualize it. And yeah, I'm a loser then if that's the case. But let's start. Let's start. Cool. There is an integer array nums sorted in ascending order, okay, with distinct values. So there's no repeating values. Good to know. Prior to being passed your functions, nums is possibly left rotated and an unknown index k. Now k ranges from 1 to the length of num such that the resulting array is this 0 indexed. For example, if this is our actual nums but it's rotated by 3 indices, what do we mean by that? So we mean that is 1, 2, 3. So we have 4, 5, 6, 7, 0, 1, 2. 4, 5, 6, 7, 0, 1, 2. This is by 3, right? Given the array nums after the possible rotation and integer array, return the index of the target if it is in nums or -1 if it's not in nums. Cool, cool, cool. So we have paused. So we're given this thing, and right, we'll solve moving zeros as well later on. And we're giving this, right? So this is possibly moved like this, right? So let's think about this very simply. If this is nums, right? If it's moved once, so the nums length of this nums is equal to 1 2 3 4 5 6 7. So 1 2 3 4 1 2 3 4 5 6, so 7. So if we do this one, I mean, let's keep this very simple. If I have, let's say, 0 1 3, if I do this one, then I will get 1 3 0. If I do this 2, I'll get, so 0 goes over there. If I do this 2, I will get 3 0 1. If I do this 3 times, I will get right, 0 1, so 0 1 3. So we get 0 1 3. So we get the original array. Right, cool. So this is one of all the possible values. So k is greater than equal to k is greater than length of num. So this is what we are dealing with over here at the moment. This could be 1 till 7. I mean, if length is 3, then this is pretty much binary search, but is equal to 1, right? Let's see if we could find certain values in that case, right? Let's take this example. If I were to do this once, right? If we were to do this once, what will happen? We'll get 1 2 4 5 6 7 0. 2. If I do this, I'll get 2 4 5 6 7 0 1. If I do this 3 times, I'll get 4 5 6 7 0 1 2. I'm just trying to see for any patterns. Right, I'm just keep on doing this. One thing you can figure out, okay, what's the middlemost value? So this is 0 1 2 3 4 5 um, and 6, right? So the middlemost value, by the way, we calculate this like this. So it's 0 plus 6 6 by 2, it's 3. So we get 3 as our middlemost value. So this turns out to be our middlemost value. Cool. And for some reason, right, 0 1 2 3, and you can see that throughout the permutation we get 6 and we get 7, right? So we get 3 as our middlemost, and says you must be at or log n. Okay, so this is 3. I mean, we could do something like log n plus log n, which is going to be 2 log n, but it's still going to be log n, right? So if I could find out the least element and the greatest element, and then I can just use that as our indexes. Maybe that my idea through this is we know how to use binary search in this, taking this as L and this is R, and then we just cross it down. If I could somehow figure out where 7 and 0 are positioned, and then use those two values appropriately. So if we have 5 over here, right? Um, how would I do this? Okay, if the element before it is, I mean, obviously the element before it will always be, unless it's there, the element, the length क्या हो सकता है, minimum 1 हो सकता है. The element before it will always be less than it. That's true. Um, yeah, he's right though. So every element to the left of it will be small, right? Regardless. So every element of the middlemost element in the array will always be small. The only variation we will see is on the right side. Right side is where we will see certain things not following order, right? So as you can see clearly, 6 is greater, 7 is greater, but not 0. 6 is 7 0 1. So what we could do is we can come again in the middlemost value over here, because we'll have 6 minus 3, which is equal to 3, which is sorry, 6 plus 3 is 9, 9 by 2. Well, that's, I mean, clearly if you not see this, we'll have 7. So now we know that everything below 7, after 7 is less than it. But how do we know that? Was is greater than 5? So LE will be less. Yeah, so I have to make more patterns with this because I'm not able to understand at all. Not able to understand at all. Like, how do I even okay, let's do another thing. Um, let's go 4. Um, right. So we do 4. We get 5, 6, 7, 0, 1, 2, and we get 4. We do 5. We will get 6, 7, 0, 1, 2, 4, 5. If we do 6, we will get 7, 0, 1, 2, 4, 5, 4, 5, 6. And if we do 0, 1, 2, 3, 4, 5, 6, 7. Something like that. I don't know. Also, this is kind of wrong. Yeah, so 0, 1, 2, 4, 5, 6, 7. Right. So that is essentially all the permutations that we can. Again, I don't know why this does that. इसको क्या लेना देना उससे? Oh, okay. So it pretty much they coded that way. Okay. Okay, let me take this down. Okay, so this is one of those permutations that we have. If we were to ever two, 2, 3, 4, 5, 6, if we ever look at the middlemost value, फिर से indentation. Um, I will also look at the middlemost value. Okay. Um, everything before it, it's always smaller than this, except in this case. Like in this case, we see some. How do I even solve this? Oh man, how do I even solve this? How is this knowledge based question? How am I supposed to solve this? Um, if I come over here, 5. I genuinely don't know how to solve this. Like, I'm thinking I should just stop the timer and accept defeat. How am I supposed to do this? Oh man. This is a sad day. I'm just watching the video solution. I don't want to waste my time, chat. I know I'm not gonna come up with this. So I'm legitimately so dumb. uh,
Okay, let's solve
wasting of time.
LeetCode 33 search and rotated sorted array. So we're basically given an array that was originally sorted like this one, but then it became rotated like this one. And by rotated, they mean that they took a certain pivot or index of the array, like right over here, and then they cut it in half and then swapped the portions, right? So you can basically think of this right-hand portion being swapped over to the left side over here, right? That's what happened, as you can see here. Right, these two halves were put in the opposite position. And we're also given a target value in this example, target 0. Is this our target? Is this our target? Is literally just check here, this is our target, and then we return the index 4. Now this is just too trivial of a solution, right? The time complexity isn't bad, it's O of n, but can we do better? In this problem, they literally tell us to find a solution that's O of log n, so obviously we can. And basically, anytime you're looking for a solution that's log n or better than linear, almost every time you're going to be looking for a binary search type solution. So since this array was originally rotated, can we use that to our advantage to potentially find a binary search type solution for this problem? Let's try to analyze it and see what we can find. So given that the original array was sorted, if we wanted to represent that as a graph, we would basically have a continuously increasing line. It might not necessarily be linear, but it would always be increasing, right? And then we took some pivot, like over here, and then swapped these halves around, right? So let's draw what that would look like. So let's say the left side was exclusively greater than the right side, because that's what it means by rotating the array, right? So I think this is a pretty good way to visualize the problem to kind of understand what it would look like. And you can use this to your advantage to find potential
Yeah, I mean, that makes
patterns
sense.
that can help us find a binary search.
That actually does make sense. This guy has some magic tree. So what he does is normally your array looks something like this, right? But after the pivot, now it looks something like, if you were to like pivot over here, now it looks something like, this, right? And that actually makes sense when you look at the
Solution. So with a problem like this, you really have to break it down into discrete cases and then use those cases to form a solution. So the most obvious thing is that there are two portions of the array, right? There's a left portion and a right portion. Both independently are sorted, right? So it's like we have two halves that are sorted. And so we know that a binary search usually has 3 pointers, a left pointer, a middle pointer, and a right pointer. The left is always going to be less than or equal to the right. This is just something you kind of know from binary search. So let's say our middle value was 6 at some point, right? This means that we're in the left sorted portion of the array. So can we use that to our advantage? So let's say our target was greater than 6. In that case, we know for sure, since we're in the left sorted portion of the array, none of these values are greater than 6. So we can basically say these are eliminated. Let's run binary search on this portion now, right? So that's pretty easy. If we know that we're in the left sorted portion and our target is greater than the middle, this is what we can do. What if our target is less than the middle value? So what if our target was less than 6? Well, these two numbers are less than 6, and these 3 numbers are less than 6. So how do we know which way to go? Do we go left or do we go right? Because we can't go both directions in a binary search. The key is to see that in our left sorted portion, the smallest value is right here, right? Or on our graph, it's right here. So if our target is even smaller than this left value, 4, in that case, we know that we don't have to search 4, we don't have to search 5, we don't have to search 6. We can run binary search over here. But if our value is greater than or equal to 4, then that means we're going to run binary search on these two values, right? It's less than 6, but it's greater than or equal to 4. So we can run binary search on these two values. We can eliminate all of these from consideration. So all of that is if we were in the left sorted portion of the array, right? Now what happens if we're in the right sorted portion of the array? Let's say our middle was 1. And let's say we knew somehow that we were in the right sorted portion of the array. What if our target was less than 1? Well, then we know we have to search the left. The only value less than 1 is right here. So we're going to search the left portion of this array. We're not going to look at 1. We're not going to look at 2 anymore. Any value to the right of 1 is greater than 1, so we don't have to look at them. We're just going to run binary search on these elements. We don't necessarily have to know where the pivot even is. We just know we have to go left. But what if our target was greater than 1? Well, then our solution could possibly be 2. It could also be any of these 4 values. So then where do we go? Again, we can use this rightmost value, or the edge basically of our array, to our advantage. So if our target is greater than 1 and it's also greater than 2, that means we can again search this left portion. We can eliminate these 2 from consideration. But what if the opposite is true? What if our target is greater than 1, but it's less than or equal to 2? In that case, we only have to run binary search on the right portion of 1, every value to the right of 1, meaning we can easier to understand once we actually write the code, but I think it's also important to visualize it and actually understand what's going on before you even write a single line of code. And knowing what we just learned, let's just go through this example of the target equal. So, and given this input array, our middle would be the right sorted portion. How do we even know if we're in the left sorted portion or the right sorted portion? Well, the way I check is just if our middle value is greater than or equal to our left, the actual value at that index, if this is true, then that means our middle value belongs to the left sorted portion. If this wasn't true, that means our middle value is in the right sorted portion, and we would write our if statements accordingly. But knowing that we are in this left sorted portion, is less than, but knowing that we are in this left sorted portion, right? Let's run through it. So our target is 0. That means our target is less than 7. So our target is less than 7. That means we could be looking here or we could be looking here. So let's compare it to 4 now. Is our target less than the leftmost value? Well, 0 is less than 4. Okay, so that means we're all good. We just have to search every value to the right of our middle value. So we can eliminate all of these. We can cross out our middle and left. Our new left is going to be here, and our new middle is going to be here. Now in this case, are we in the left sorted portion or the right sorted portion? Well, among these 3 values, the entire array is pretty much sorted. So according to our if statements, we're basically going to say that middle belongs to the left sorted portion because the entire thing is sorted. So now we compare middle to target. Well, our we only have to go left. A visualization, and we have 1. Imagine we're given an array equal in that case, and we still have to check that one value. It says, imagine we're given our condition is while left is less than or equal to right, because imagine we're given an array the average of them. If it is, we simply return the int. If that's not the case, then we need to check which portion of the array are we in. Are we in the left sorted portion? And like I mentioned before, we can check that if the middle value is greater than the left value. Well, greater than or equal, right? Because it's possible that the middle value and the left value could be the same value. The else condition would be that we're in the right sorted portion. So the simplest case is that our target is greater than the middle value. In that case, we're going to search right. So we can
Okay, so we have middle and we check that. Now we check whether we're in the left side portion or not. How do we check it? We check it like that. That makes sense. Cool. So we're in the okay, if is the target greater than equal to nums dot mids?
Say our left pointer is now going to be mid
Mids
plus
plus
1.
1.
So if the target is actually less than the middle, then we need to do something else. So if the target is less than the middle, but it's also less than the leftmost value in nums, then we also have to search the right portion. So we're going to do left is mid plus 1. Now notice how these two cases are evaluating to the same thing. That means we can condense them. We can get rid of this
And say
and
or.
say instead if the target is greater than the middle, or if the target is less than the leftmost value. Then we have to search the right portion, so we can get rid of this. And if this isn't true, that means the target is less than the middle, but it's greater than the left. That means we search the left portion, so we
Should we
can
say
update our
right?
right pointer. I had a typo over here. We're not calling it left, we're just calling it L for short. And so this is if we were in the right sorted portion of the array. The easy thing is if target is less than the middle, that means we go left, so we can update our right pointer to mid minus 1. Then middle, and the target, that means we have to go left as well. In the middle, in that case, we only value is that the target is greater than the middle value and the target is less than the right value. In that case, we return it up here. And just as I expected, because I just finished this problem like a half hour ago, it worked perfectly. So this is not an easy problem. The code looks pretty easy, but you really have to understand.
Ah, yeah, this is much better. Ah, mashallah, maza aa gaya. If num's target is less than this, then we know, okay, cool. 3 plus years is crazy, chat. So I think the idea behind this is that so we'll have L is equal to this, R is equal to length of nums minus 1, while length is greater than equal to R, middle is equal to L plus R. Am I sad? Yes. Yes, I am. Right. If nums middle return middle. Else you wanna check if we are in the left sorted half, um, we are in right sorted half, we check with. So if we are on the left sorted half, how do we check that? Um, if nums L is greater than or equal to nums, right, right. So if nums L is greater than or equal to, we know. If we are in how do we check this? But how do we know if we are in the right sorted half, so to speak? If you're in the right sorted half, that means nums middle is less than or equal to nums are, so to speak. The reason why I say this is because normally we had something like this. We split it in half. That means अब ये यहाँ से यहाँ जाएगा and ये यहाँ से यहाँ जा रहा है. So if we are in the right, if we are in the left sorted half, this will be less. But if we are here, right, if we are somewhere over here, this will be ज़्यादा. Right, so I'm right. Okay. Right, so if we are in our left sorted half, we'll do something, and if we are in the right sorted half, we will do something. Return -1. Um, right, so if we in our left sorted half, let me just draw that diagram. If that diagram helped. So pivot somewhere over here. Right, if the reason why you want to even check this half is if yeah, if num l greater than equal to target, um, if this is the case, right, if nums, like, then we would do something like r is equal to middle -1, right? If not, then we would say l is equal to middle +1, right? Let's assume we are over here, and right, how would we want to check if this is over here? So if nums middle nums are, if that is the case, if it's within these range, and we start from here, yeah. If not, we will do that, right? Right, so if this is in this range, so to speak, we will do l is equal to middle +1. Else, if this if it's not in this range, so to speak, like, we'll do l equal middle +1. If it's not in this, then we'll say r is equal to middle -1. Okay, I think I'm understanding how this is working. Like, I think I'm understanding how this works. So, to be honest, like, I think I understand how this is working. Okay, yeah. So I think I understand how it works right now, and it's very simple. So imagine we have a sorted list, right? Imagine we have a sorted list, and the moment we say we are like we're basically pivoting it, what we're doing is we are essentially doing something like right, so let's just make so if, let's say, this is the element we are pivoting by, so this is our some element we are pivoting by. The moment we pivot this, right, what would happen is, like, imagine this is a maximum element, right, and we pivot it, right? If we pivot it, sorry, wait a minute, chat, wait a minute. um, right, if we pivot this, right, if this goes down, let's go take this down, right, if we pivot that to some element over here, if we pivot that, what would happen is, so now this will start from here, and this will start from here, right? So just to give some numbers, let's say if we were over here 4, we were like somewhere over like 4 7 0. Now we will have 4 7 and we'll have 0, and now we could have 4 in this, but let's say we can have 3. So this is what we're doing, right? And so, right, and so right now the length still remains the same. So what we can do is we can something, we have L is equal to 0, R is equal to length of nums minus 1, and then I can say Y length is greater than equal to R. We are essentially saying that this is our list, so to speak. Now we are putting our L over here and we're putting our R over here, and we'll be pushing towards some middlemost value over here. Now we don't know what that middlemost value could be depending on the permutation slash combination that we have. Over here the middlemost value turns out to be 0, right? So that's our middlemost value. So we say middle is equal to L plus R equal to 2. Now it could be that stroke of luck key we check and this turns out to be this. We can say if nums middle is equal to our target, we will just return middle. That is great. Now what we want to check, if that's not the case, right? So what we want to check is something, um, left sorted half, um, we are in right sorted half. How do we check this, right? How do we know the number that we landed in is in? So let's say if we were to land on, let's say not this, but let's say on 7, so like, and this was like, let's say something 6. So how do I know if the number I am in is like on which side it's sorted? One of the easiest things you can do is on the this case, on the left sorted case, if this was supposed to be 7, this is supposed to be 6. If we found out, yeah, this is 7 to be honest, like, I mean, if we found out key 7, because you see, like, this will always be sorted, right? So what thing we can say is very easily, we can say nums L is less than equal to nums middle. This is our tail that it works. How do we know? We know this because you see the, now if we were to take this normal case and this was 0 and this was 7, how would we know that? Well, we would know that very easily, because our nums middle would be less than or equal to nums r based on the graph, right? So we would know that, right? And the reason why we do equal to is maybe the length of the list is 1, so that could also be the case. If this is the case, then we know we are in the right place. Now if we know this, what we can say is if nums L greater than equal to, if it's somewhat equal in this nums middle, but it's technically not equal to middle, because अगर होता तो हम लोग क्या कर सकते थे, we can say R is equal to middle minus 1, right? Because यहाँ पे middle है, इन लोगों को यहाँ पे हम लोग close down करना है, right? So if nums L, then we can do this. If is this is not the case, इसके range में ला ही नहीं करता है, then we can say L is equal to middle plus 1, right? Now imagine if we are over here, right? If we are this, so what we could say is, you can say nums middle less than equal to target. We can say less than equal to nums r. If that is the case, we can say L is equal to middle plus 1. Else if that is not the case, if it's not here, we can say L is equal to middle minus 1. And the moment this happens, it will again then just recalculate it from there. If we run this, right, and if we submit this, yeah, this works surprisingly fast, right? It's able to bite it, do it in 0. So yeah, I think we understood the logic. This really helped. So now it will come over here and it will like left and r, and we'll check again. Like if r is equal to middle minus 1, right, this happens, and then we'll come here and we'll say, okay, middle is that, and it is equal to, else we'll check whether p and the sorted are right half, because it could change, right? This could pretty much, we could in a sense be that, right? Interesting question, I would say. Yeah, move 0. Yeah, this was an interesting question. Again, I solved this. um I hate my life. Yeah, okay, anyway, let's not do that. Let's not go into hating your life and all that. So we wanna essentially, what we wanna do, this is just, this solution is very bad, so to speak. It's also ugly to look at. We just wanna shift all the zeros there. And so how would want to do this? I think someone said try looking. So this is our array. So yeah, let's try to solve this on this array. And so if we have an array like 0 1 0 3 12, instead of thinking I want to shift all the zeros to the right, I want to shift all the non-zeros to the left. Right, so if I have a pointer on the left that points at all the zeros, and I keep looking for the right pointer, so like, okay, fine, yep, swipe, okay, right, now I go to left. Again, I don't really know how am I supposed to solve this, right? Like how am I, like how am I, I mean, I did this, I'm just doing this to see if I can solve this. um this is kind of dumb. How would we, like, this thing, I'm so embarrassed that I'm not able to solve certain questions. Like, it kind of makes me sad. Hmm. How would we solve this in O of n time complexity? So if we, like, let's just say L, and I keep another pointer R, I'm like, oh wow, that is that. So I swipe them, so now it becomes 1 0 0 3 12, and then I come over here to left. And obviously now I'm looking at a, right, I swipe this. Now left is over here, now the right has to look for appropriate. Right, so now it has 1 3 0 0 12. I think one thing that we can do is, while, okay, so now this swipes it, so that means we're just swiping it. Instead of swiping it, I mean, that's the naive solution, right? So now it swipes there and goes to the next and tries to find. Again, how do you solve this in of n time complexity? One answer could be try to make an index. Yeah, I mean, I don't know how is that gonna work really well. It's gonna be more complicated. Solution has to be simple, chat. Giving a complex solution is not easy. Giving an easy solution is very tough. This is, Again, man, I don't want to look at the solution and solve it. That shit has no merit. I'm so confused. How is this? Let's look at that. What do I mean by Such a loser, bro. Uh, chat. Which resets? Oh wow, really. Um, God knows which. I mean, I just such I don't know what to say, to be honest. I'm kind of sad. Um, but yeah, I don't know what to say. Yeah, let's try to solve this because now we have sorted a similar type of question. So now we have a bit of context of how we can do this, right? By the way, this was my finest solution in this exercise, but obviously that's not right, so to speak. But anyhow, let's see. So we have an array sorted in ascending order written between, for example, yeah. So we have the same setup, right? We have the same setup as this before. And now our job is to to find the most minimum element in overfence. So let's assume, so this is our minimum element, right? I mean, this is clearly easy to see, but the moment this becomes pivoted, I mean, this is lift pivoted, right? uh yeah, seems like it. So pretty much like 4 5 6. Great, so this is left pivoted. So this pretty much what happens is now what happened is we pretty much took this and we were like, yeah, we'll put this over here, so 7 becomes 4, and now this is equal to 3 and this is 0, and we can get the middle element anything, so to speak, right? So how do we do this? What I think is important is, okay, so but this is the middlemost element, right? But how do we find it? What I am thinking is, what could be the value, right? So I was thinking of having a min element, and let's this be equal to, because maximum is that, so we can say minus 5001, right? And I think my understanding with this is, we'll say left is equal to 0, r is equal to length of nums minus 1, and I'll say while left is greater than or equal to r, right? right? And if we'll have some middle value, which is, and so I think my idea with this solution, I think I know what to do, right? And this may sound a bit weird, but if num's middle is equal, because then it never truly be equal to middle, um, right? But I'll say that if it's equal to the min element, then great, we can return middle. Okay, return the minimum element, so we can, well, that's great. So we can return num's middle. Um, like how can I use this? Because I feel like it's on my fingertips. Um, um, how do I figure this out? Um, I mean, if I know this case and I know I'm in the right sorted half, right? I'm on the left sorted half, and so I need to be checking this on the right sorted half because the right sorted half will be the one that is pivoting on that side. So I feel like if that is the case, also let's just return the min element. If we are on the left sorted half, that means we need to go check on the right sorted half because that is the one that we know contains that. And so how do we know we're in the left sorted half? If nums L is greater than or equal to nums middle, so that means we are in the left sorted half, right? We'll do something. Um, we are in the right. We are in the right sorted half, and we know we want to be in the right sorted half, right? We don't want to be in the left sorted half because we know the left sorted half will not contain the minimum element, right? As you see, this is the left sorted half and this is the right sorted half, and so we don't want to be over here, right? This is not where we want to be. And so we would say something of L is equal to middle plus 1, right? Because as we like get off here, else right now we are in the right sorted off, right? I'm in the right sorted off, and we'll check um we're in the right sorted off. Right, that means we are in the right sorted off somehow, right? And we just write this because my we said nums middle is greater than or equal to nums are. So right now we are in the right sorted half. And this is where we make the decision, so to speak. Um, um, if nums middle is less than minimum element, then we'll say minimum element is equal to nums middle. If my nums dot middle is less than my minimum element, we'll say middle or that. else, which could be the case that num's middle is greater than or equal to minimum element. Because if that is the case that it's greater than that, um, um, because if that is the case, then I would want to do middle minus one. But if it's greater than that, then that's kind of shit. That is kind of shit. If it's greater than, we would do the same. We would do the same thing. We're doing the same thing, right? Um, and because if this is less than the minimum element, that's great. We know we'll find even more than this. But if it's greater than that, if it's if our minimum element is, I would assume you would do the same thing, right? Right? I would use you to r is equal to middle minus one because you would be like, okay, nahi, skip. Um, wait. Let me see this code real quick, chat. Um, we don't want to be in the left order. We want to be in the right order now. That's what we really worry about. Um, um, yeah, that's a bit confusing. I don't know, man. I'm actually dumb. Fuck. Um, uh, um, the mental clarity is not there, right? Yeah, I know. Um, I think I know what to do. What I want to do is if nums r is if nums r is greater than the minimum element, right? If it's greater than the minimum element, then we would. I want to do that. Yeah, I won't solve this because it's like just trying to dig a hole larger than this. मुझे यही समझ में नहीं आया. I'm trying to go ahead and try to solve something else. God, it's so tough. I am on my right sorted half. This is the right sorted half. Yeah, I'm gonna. It's kind of sad I don't do this, but I'm just like, I'm just like so like, um, I don't know what to say. I'm kind of sad to be honest. I was kind of expecting more. Yeah, but I will check this up tomorrow. Yeah, thank you for tuning in for another late night session. But yeah, it's kind of sad. I thought I would get more done, but anyhow, we do what we gotta do. Bye bye, chat. See you later.